Okie doke. So onward and upward into more neutral geometry. On today's show, three very important geometric inequalities. No, not that. Three very important geometric inequalities. Relationships between sides, relationships among angles, how they interplay, how triangles work. So here they come. The scalene inequality. The scalene inequality says that in any triangle, the greater side lies opposite the greater angle, and the greater angle lies opposite the greater side. So let's just establish what we mean by that. We mean that if we have a triangle ABC, if AB is greater than BC, then that if and only if the measure of angle ACB is greater than the measure of angle BAC. It's an if and only if, which means we have to go one way and then the other. I'll go the one way here and the other way in class. We'll go this way first. We'll assume that AB is bigger than BC, and we'll show that angle ACB has to be bigger than angle BAC, and I'll walk us through that. So if AB is bigger than BC, then there's got to be some point, call it D, between A and B, such that BD is congruent to BC. And we're going to connect the dots. Well, what does that mean? That means that the measure of angle ACB has to be bigger than the measure of angle DCB, because D is in the interior of angle ACB. And so that kind of comes along from the protractor postulate with the betweenness property of rays, so we're good. But by isosceles triangle, the measure of angle DCB is equal to the measure of angle CDB. So far, so good. So far, so good. But the measure of angle CDB has to be bigger than the measure of angle CAB. Because in this here red triangle, that thar angle is an exterior angle. So it must be strictly greater than either of the remote interior angles. And therefore, the measure of angle ACB, which is greater than DCB, which is equal to CDB, which is greater than CAB, has to be greater than the measure of angle BAC or CAB. It doesn't much matter. And we've got the what we want. So if one side is bigger than another, its opposite angle will be bigger than the other opposite angle. Make sense? Makes sense. I will go the other way when we come together in class. We'll prove that if one angle is bigger than another in a triangle, that the bigger angle is opposite the bigger side. Okay? Inequality 2 is the familiar triangle inequality from high school. You remember this. In any triangle, AC is less than AB plus BC. That is to say, in any triangle, the sum of any two sides is bigger than the third. So let's do it like this. I've got a triangle ABC. AC is not as big as AB plus BC. Is it true in neutral geometry? Well, I think we can pull this off. We can extend ray AB. We can extend it to some point D such that BD is congruent to BC. Ruler postulate says I can extend ray AB as long as I want, and one of those points on the other side of B from A has to be such that BD is congruent to BC. Must. Therefore, connect the dots, the measure of angle ACD is greater than the measure of angle BCD, because B is in the interior of ACD. But wait a minute, BCD is just as big as ADC. Well, the scalene inequality says that if this big red angle is bigger than that puny green angle, then this opposite side has to be bigger than that opposite side. So AD has to be bigger than AC. But AD is just what you get when you add AB and BD. And oh, wait a minute, BD is the same as BC. And now I've got what I want. The triangle inequality works even in neutral geometry. You do not need the Euclidean parallel postulate to prove the triangle inequality. Big theorem 3 is called the Hinge theorem. The Hinge theorem says if triangle ABC and triangle DEF are two triangles such that AB is congruent to DE, AC is congruent to DF, and angle BAC is less in measure than angle DEF, then BC must be less than EF. Picture time. Here's the claim. If this angle is smaller than that one, then this side has to be smaller than that one. That's the way this goes. That's the way the Hinge theorem goes. So the Hinge theorem comes third because we need the others to get it, and this is the way we're going to get it. We are going to construct triangle ABG congruent to triangle DEF. And we're going to prove that BG has to be bigger than BC. That's the plan. And here's how this goes. There has to be a point somewhere out here such that if I connect the dots, triangle ABG is congruent to triangle DEF. There has to be. We know that. There's a theorem that you proved that guarantees that. So this segment BG has to cross this ray at some point. We'll call that J. It's guaranteed by the crossbar theorem. J is not C. If J is C, we're done. So we'll say J isn't C. And then we're going to give you an angle bisector. Here's an angle bisector to a point H, angle bisector. And I know that AG has to be congruent to DF because triangle ABG is congruent to triangle DEF. So looky what I got. I have triangle AHC, which doesn't even exist yet. There it is. Congruent to triangle AHG because it's got the double marked sides, it's got an angle bisector, and it's got this thing congruent to itself. So therefore, HC is the same as HG. And that's good because I know from looking at the picture that BH plus HG is BG. That almost makes sense. But HG is the same as HC. And that means by the triangle inequality, BC is less than BG. There it is. BC has to be less than EF. The Hinge theorem is one of my favorite theorems because this makes the side-side-side triangle congruence work out much more nicely. You go back to side-side-side. You were thinking, how am I going to get that angle to work? Well, if that included angle, pick any two sides. If that included angle in the one triangle is different than the included angle in the other triangle, then the opposite sides must have different lengths. And by hypothesis, they have the same length. So those are the three big inequalities. There are some very interesting consequences of these that I will outline for you if I can. So let's pretend. Give you a line L, point P not on the line, and we're going to let F be the foot of the perpendicular. We know that there has to be a perpendicular, that it is unique, called that foot F. Here's my claim. If I pick any other point, call it R, any other point, on the line L, any point other than F, this distance, PR, must be greater than PF. This is something you will prove when we get to class. It's not a hard proof, but you will prove it when we get to class. And there's a very interesting consequence of this theorem. This establishes that the shortest distance between a point and a line is along a perpendicular. And if the shortest distance between a point and a line is along the perpendicular, we just say that the distance from a point to a line is the distance along the perpendicular. It's a very nice thing to have handy. Here's the other thing that's very nice to have handy once you establish distances between points and lines. Take any angle BAC. If a point P is on the angle bisector, a point P, here we go, here's the way we're going to say it. P is on the angle bisector of angle BAC, if and only if the distance from P to line AB is the distance from P to line AC. And this will be another theorem that you will prove when we get to class. And it goes both ways. If P is on the angle bisector, then this distance has to equal this distance. So we assume angle bisector and we show that those are congruent, but also if I have some point P and the distance to this line is the same as the distance to that line, if those match, then I'm on the angle bisector. We have to go both ways with that. We have to show if you're on the angle bisector, then the distance to each ray is the same. If the distance to each ray is the same, then P is on the angle bisector. You could probably hammer that out before you even stop watching the video. I think you could probably do that if I were to talk for another 15 minutes or so, but I'm not. And so that is section 4.3. That is three very important inequalities that relate angles and sides. There you go. I'll see you soon.